All right, here is a requested homework explanation from the Orbit's homework, and it's about a satellite in circular orbit. And this is almost exactly like the International Space Station example from the video lesson. And the thing that makes this possible or easier to do, or hey, my tablet isn't working. I stole the USB cable to connect to one of my phones. There we go. The thing to do to solve this example is to do this first, and then this, and then this. And basically, we know that yeah, I can do these in different colors. To do part one, we know that the force of gravity is equal to the force of Newtonian gravity is equal to capital G, mass of the nearby planet, mass of the object over r squared. And we have to use r equals the radius of the Earth plus h, because our diagram here is there's Earth, the blue planet, and here is radius of the Earth, which I have on the equation sheet as 6371 kilometers. Here is h, and here is our object. And the thing we need for the equation is the distance from the center of the object to the center of the Earth. And then the other part of this is F equals F net equals ma. And this force of gravity here, that is an ugly arrow. This force of gravity here is the only force. So then A is everything in the force, G m over r squared, except for the little m, because it's canceled out by the little m there. So that makes it easy to calculate the acceleration of an object that is in outer space, as long as there's no like rocket engines firing at the time, because that would be an additional force. Then for part two, we use a equals v squared over r, because it's circular motion. So this object is heading in a circular path here, and there's some velocity v going that way, and that velocity is related to the acceleration. And don't forget that we have to convert because this velocity is in meters per second, not in kilometers per second. And then finally, for part three, you want to use v is 2 pi r over the period. And again, you have to convert because this t is in seconds, and this v in meters per second. So you want to use the the raw meters per second value you got out of part 2 in order to solve part 3. But when you give your response for part 2, you want to make sure you give a response that is in kilometers per second. So your internal number for calculation purposes and your announced number are slightly different. You announce a sometimes rounded, but sometimes different units version of the quantity. So if you want to see a detailed numerical overview of that, then you want to go to the video lesson on Newtonian gravity in orbits, which includes the International Space Station as an example, which is at an altitude of 400 kilometers, as I recall. And um, I want to show you something, even though it's in the video lesson. I want to show it anyway. Um, under my weather bookmarks, heavens above, tamucc. Bring that over here. Share that. So this is a website that tracks lots of satellites that are in orbit around Earth. And one of the satellites that is in orbit is the International Space Station. And apparently it's not going to be visible in our sky for a week or so. But whenever you see a negative brightness in astronomy, it means something is really, really bright. Negative brightnesses are much brighter than positive brightnesses. And the other cool thing here is there is a height of the International Space Station graph, and you can see that the height of ISS is somewhat variable. It has these boosts of height, occasional drops of height. This is the first time I've seen one of those, but it also has this gradual drop of height. So the gradual decrease is not because it's falling, it's because it's slowing down due to air resistance. It's 400 kilometers up, which means its space is almost a vacuum there, but there's still a tiny bit of air, and that tiny bit of gas is just enough to make it slow down. The boosts are the rockets of the International Space Station, boosting it into a slightly higher orbit. And then they're at random intervals because they're used to dodge space junk. And apparently there was some space junk in the way around this time. So they actually dodged downward instead of just dodging upward like they normally do. They must have plenty of fuel, or maybe they had to come down lower in order to make a rendezvous with a rocket that was coming up. So I think thinking about the height of something that's in orbit is pretty cool. Um, you know, so that is the review of orbits for today.